Hey guys, so this is Unit 8, Part 1. The first thing that makes Unit 8 different is, oh, my bad, is it continues with our T-charts that we learned in Unit 7, but it takes it a step further. In Unit 7, we always were using the same compound or the same chemical, and so it always stayed a one-step problem. However, with stoichiometry, a balanced chemical equation has these coefficients, right? 4, 3, and 2. And so what it tells us is it tells us the ratio, the exact ratio that chemicals need to combine in order for a reaction to occur and exactly how many moles of it will produce. And so this 4 means 4 moles of aluminum, 3 moles of oxygen, and 2 moles of aluminum oxide, right? And so if we're talking about a mole ratio, okay, one of the basic things, if I want to know the mole ratio of aluminum to oxygen, it would be 4 to 3. 4 moles of aluminum to 3 moles of oxygen. If I want to know the mole ratio of oxygen to aluminum, it would be the reverse, 3 to 4. Okay, and it's based on the order of what they ask you for. If I want to know the ratio of oxygen to aluminum oxide, it would be 3 to 2, right? It's all based on these coefficients that are in the front, which in first semester we learned how to balance and put them there, and now we understand why. That it is the exact ratio needed in order for the reaction to occur. If you have less than what's needed, then the reaction won't happen. You have to have things happen in the correct amount. And so we use these mole ratios to help us do some conversions. So the first kind of conversion, and we're going to need our equation down here just to help us see so we don't have to keep scrolling. But we can use it to change from moles of one chemical to moles of another. For example, if we know that we have 10 moles of aluminum oxide, we can figure out how many moles of aluminum we need in order to create that amount. Okay, so here it says how many moles of aluminum are needed to make 10 moles of aluminum oxide. And so we see that we have a different chemical. We start with, we have aluminum oxide, we want to know aluminum. So we set up a T-chart. Okay, and so we have 10 moles of aluminum oxide, which is Al2O3, and we say, okay, if I know I have moles of Al2O3, I put moles of Al2O3 on the bottom because that's our pattern. And when you put moles on the bottom in a problem where you know you have to switch to a different chemical, you go to your balanced chemical equation. So I know that there are 2 moles in the equation, and whatever is on the top part of this column has to also come from the equation. Now, I don't care about oxygen in this question because all I'm talking about is aluminum and aluminum oxide. So I would put my 4 moles of aluminum on the top, and we will go ahead and solve because I know that this is what I want, so I can go ahead and do that. So it'd be 10 times 4 divided by 2, which 10 times 4 is 40, divided by 2 is 20 moles of aluminum. So if I want to make 10 moles of oxide, I need 20 moles of aluminum to create that amount. And in our second question, it says how many moles of aluminum oxide are made. So this time we're trying to find moles of aluminum oxide when 2.5 moles of oxygen, which I wrote the word moles there twice, are reacted with excess aluminum. I don't care about aluminum. I know what I want. I know what I have. I have 2.5 moles of oxygen. Now it's not just O, it's O2 because it's oxygen by itself is written as O2 in the formula, or in our equation, excuse me. And I put moles of oxygen on the bottom. I know I'm switching to a different compound, so I go ahead and say 3 moles of oxygen, and I could either put 4 moles of aluminum or 2 moles of aluminum oxide, and since I want aluminum oxide, I put 2 moles of aluminum oxide. This cancels out. 2.5 times 2 is 5. And then 5 divided by 3 is, let's see, 5 divided by 3 is 1.67 moles of aluminum oxide. Okay, so that's pretty good there. So in a mole-to-mole question, you're only using your mole ratio. It's a one-step problem. So let's look at what happens if we have moles of one thing, but we want to figure out grams of another, right? Because in a lab, we don't really measure on a scale with moles. So grams is really what we need. So how many moles of oxygen, and so moles of oxygen is what I'm looking for, are needed to fully react with 100 grams of aluminum? Well, if I have 100 grams of aluminum, we just set up our T-chart, okay? We say, all right, we follow our pattern. Grams of aluminum goes on the bottom. And I remember from Unit 7 that anytime we have grams in a T-chart, we go to our periodic table for our molar mass. Well, the molar mass of aluminum is 26.98, and we know that molar mass is always equal to 1 mole of aluminum. So, we're not done though. This 1 mole of aluminum, or moles of aluminum, does not match what I want, and so therefore I have to keep going in my T-chart. I just repeat the pattern. Okay, so I bring moles of aluminum down here. Now I've already used my 1 mole of aluminum. If I have moles of aluminum on the bottom and I know ultimately I need to change to oxygen, now is when I use my mole ratio and go to my equation. So I say, okay, 4 moles of aluminum, and I could either put 3 moles of oxygen on the top or 2 moles of aluminum oxide. I want oxygen, so I put 3 moles of O2. Now, moles of oxygen is what I want, and so therefore I can stop and I'm done, and I just plug it in to my calculator. 100 times 1 divided by 26.98 times 3 divided by 4. So when we put that in our calculator, we have 100 divided by 26.98 times 3 divided by 4 gives us 2.78 moles of oxygen. Okay, so that is how many moles we would need in order to fully react. Now, key thing here to note is if you're looking at, if you have put a number from your equation into your column, then the number that goes on top also has to be from our equation. Okay, don't be tempted to put the 4 there. Okay, it doesn't belong there. Grams always has 1 mole, and then your moles from your equation are always on top of each other. Okay, so try to keep that in mind. Now if we look at the next question, excuse me, says how many grams of aluminum oxide are made by 10 moles of oxygen? So we have 10 moles of oxygen, now we want grams of aluminum oxide. So I start with 10 moles of O2, and I put moles of oxygen on the bottom. Now I've put moles of oxygen on the bottom. I know that I want to switch to aluminum oxide, so that means I go to my equation and I say, okay, there are 3 moles of oxygen in my equation, and they make 2 moles of aluminum oxide. And I would be done if they wanted moles of aluminum oxide, but they don't. The question is asking for grams, so that means I keep going, and I repeat moles of aluminum oxide. And I've already used my 2 from my equation, and all I need to do is change it into grams, right? I'm keeping the aluminum oxide part the same. I'm changing moles to grams, and I know that 1 mole is always equal to my molar mass. And so the molar mass of aluminum oxide we would have to calculate. So we have aluminum, we have oxygen, 2 and 3, 26.98. Oxygen is 16. 3 times 16 is 48. And let's see, 2 times 26.98 is 53.96. So added to 48 gives us a total of 101.96. So that is where we write with grams, 101.96 grams. So 10 divided by 3 times 2 times 101.96 gives us 679.73 grams of aluminum oxide. So that would be quite a lot. And so with these two-step problems, the hardest part is remembering, okay, when do I need to use my mole ratio and when is it just 1? And so pay attention to that little trick I talked about how if you use a number from the equation, the number on top also has to be from the equation. Okay, so let's go with the longest of the problems. If we're changing from grams of one thing to grams of something else. So in this case, we're going to be using 2 molar masses and 1 mole ratio, so it's kind of a 3-step problem. But it says how many grams of aluminum oxide are produced by 50 grams of aluminum. So again, we always start with what we have. We have 50.0 grams of aluminum. And I know that if I start with grams of aluminum has to go on the bottom. And anytime I have grams, I go to my periodic table. The molar mass of aluminum is 26.98, and it's always equal to 1 mole of that same compound. And since moles of aluminum is not what I want, I repeat my pattern. So I have moles of aluminum on the bottom. And since I've already used 1 mole of aluminum, I'm now going to go to my equation to change 4 moles of aluminum into 2 moles of aluminum oxide. Okay, and then I repeat my pattern and bring moles of aluminum oxide down here. And all I need left to change it to match what I want is grams of aluminum oxide. And we know that anytime I see grams, I go to molar mass, and we said that the molar mass of aluminum oxide was 101.96, and it's always equal to 1 mole. And so we just do our multiplication. So it would be 50 times 1 divided by 26.98 times 2 divided by 4 times 101.96, and that will give us 94.5 grams of aluminum oxide. So, yay. That's how you do that one. And then the next one, how many grams of oxygen? So we want grams of oxygen are needed to fully react with 15.8 grams of aluminum. So again, we start off with what we got. We have 15.8 grams of aluminum, and we repeat our pattern. We put grams of aluminum on the bottom. Anytime I have grams, I go to the periodic table. So 26.98 grams is equal to 1 mole of aluminum. We repeat our pattern and put moles of aluminum on the bottom. And this time we go to our periodic table. We change, our balanced chemical equation. We put a 4 moles there. We put our 3 moles of oxygen on the top. We bring down moles of oxygen and switch to grams of O2. Now here's the thing. You're going to want to remember that because oxygen is O2 when it's by itself, that changes the molar mass from being just 16 to being 32. That's a common mistake on the test, so you're going to want to look out for that. And so now we just say 15.8 divided by 26.98 times 3 divided by 4 times 32 gives us 14.05 grams of oxygen. And so these are your T-charts. Everything that we did involving T-charts from Unit 8. So keep an eye out for the next video. It will be Unit 8, Part 2.